So we're going to get started with the ACS AstroCheminars for the month of November. Thanks for joining us. I'm the chair of the Astrochemistry Subdivision of the ACS, Heather Abbott-Lyon, and I'm joined today by the past chair, Partha, and the vice chair, Chris Bennett, who's working on the Zoom for us, and Kyle Crabtree, who is our chair-elect. So this afternoon, I have the great pleasure of introducing Shane Goettle, who's a third-year graduate student with Ralph Kaiser at the University of Hawaii, and he will give his talk.
Thank you. Let me share my screen. All right. Let me minimize the picture bubble. Okay, so I will be talking about the reaction dynamics of two simple silicon and sulfur containing species, silane thione and the thiosiloformal radical. Okay, so let's just jump right in. My reason for studying these silicon-sulfur molecules lies with astrochemistry. Multiple silicon and sulfur-containing molecules have been detected in the interstellar and circumstellar environments, but the fundamental reaction mechanisms by which they are formed are still largely unknown. So these processes show significance in initiating a series of elementary chemical reactions, leading eventually to complex molecules or precursors to interstellar grains. In the interstellar medium, so far, 13 molecules containing silicon and 32 containing sulfur have been observed. However, only one molecule containing both silicon and sulfur has been detected, silicon monosulfide. But then, what about other simple silicon sulfur containing molecules? They haven't been observed, but are they formed? And if so, how? So to explore this, I chose these two reactions where we have the silylidyne radical with hydrogen sulfide to form H2SAS and silicon with thiomethanol to form HSAS-SASH. And so SIH only has a tentative detection toward the Orion-Kleinman-Low Nebula. However, H2S and thiomethanol both have multiple interstellar detections. So it stands to reason that these reactions may occur. So in this study, I used the crossed molecular beams technique to study the reactions of the silylidyne D1 radical with deuterium sulfide, as well as with hydrogen sulfide as a partially deuterated case to get information on H or D loss, as well as the silicon plus thiomethanol reaction. So this is a top view of the experimental setup. So we have a large stainless steel box that houses two source chambers. In each of these, we generate a reactant supersonic molecular beam, which then collide in our main chamber. And then these products scatter and are detected by a rotatable universal detector. So in a little more detail for our experimental procedure, our reactant gases are each pulsed through a small nozzle to attain supersonic expansion. Our silicon beam is generated by laser ablation of a rotating silicon rod, which is then seeded in a neon gas. To create the SID beam, we use a neon deuterium mixture as our seeding gas, which also acts as a reactant gas in which our ablated silicon then abstracts a deuterium from the deuterium in the seeding gas. And then our secondary gas is just pure. So we either use D2S, H2S, or CH3SH, depending on which of the reactions we did. So after, once inside the detector, our products are then ionized by electron impact ionization at 80 eV. And then they are filtered by a quadrupole mass spectrometer, then enhanced by a daily type detector. And so the data that we obtain consists of time of flight spectra obtained at different angles. And then from this, we can obtain a laboratory angular distribution by using the time of flight data at each of these angles. In order to get more information on our system, we must transform our laboratory data into the center of mass reference frame. To use this, we use a forward convolution routine where we estimate values of our center of mass, angular flux distribution, and translational energy distributions, which I will talk about in a bit. But from these, we estimate values to calculate go back and calculate the time of flight spectra and lab angle distribution, which we see as these fit lines. So this is an iterative process in which we change parameters to eventually get a decent fit of our data. So let's first take a look at the silicon plus thiomethanol system. Here we scanned at mass to charge 61, corresponding to an HSAS or SASH product in a methyl loss channel. We also scanned at mass to charge 75 and 74 for H and H2 loss, but saw no definite signal. So here we have the lab angular distribution, shows the integrated counts of our ionized products at each angle taken, with a center of mass angle of 54 degrees. This dip here at the center of mass is indicative of an indirect reaction involving geometric limitations. Underneath this, we have our time of flight spectra at 6 different angles. We can see reasonable fits of the data here. We can get more information on the system by constructing a Newton circle diagram. So this uses our reactant velocity vectors to get the maximum velocity of our product in the center of mass reference frame, denoted by the circles. With this, we can predict our laboratory angular distribution of desired products by superimposing the Newton circle for each product channel. So in this case, we can confirm that we have to get signal from a channel other than H loss, since the Newton circle is very small angular range, but we see signal at much lower angles than is shown. So here are the center of mass functions that were used to fit the data. And so first, we have the translational energy distribution. The conservation of energy dictates that translational energy is equal to our collision energy minus reaction energy, minus internal energy of our products. However, at the maximum translational energy, we'll have no internal excitation of our products. And so using this value, we can then recover a reaction energy, in this case, negative 70 kilojoules per mole. And after comparing it to calculated values for this reaction, we can see that the energy matches the HSIS isomer. Next, we have the center of mass angular flux distribution. This describes our product scattering probability at an angle theta. with respect to the relative velocity vector between our reactant beams. And so in this case, we have coplanar scatter, which indicates an indirect reaction. The dip at 90 degrees shows geometric limitation and emission of our methyl group perpendicular to the angular momentum vector. And this is visualized over here in a flux contour map, which is dependent on the product velocity and angular distributions. Our laboratory experiments were coupled with electronic structure calculations as well. And so here we have the computed triplet potential energy surface with a collision energy of 12.8 kilojoules per mole. Products P1 through P4 could be formed. However, as I showed in the previous slide, our experiments show the formation of at least product P1, the HSAS radical. So we see that there is no experimental evidence of P2 or P4 since we saw no signal for H-loss channel. Plus, there is also a high barrier for the methyl migration, which would be inaccessible in cold environments such as molecular clouds. So the most likely pathway then involves silicon addition to the sulfur lone pair, and then hydrogen migration, which is followed then by a methyl loss to form P1. Our RKM calculations were also performed at a collision energy of 0 kilojoules per mole to better simulate these cold environments. And the branching ratios obtained show that we almost exclusively formed product P1. So now let's move on to the second system. So SID plus D2S. First, we tried to collect data at mass to charge 64. However, there was really high background, so we could not do this. But then we took data at mass to charge 62. However, there are 3 possible contributing reactions here. We could get signal from a fragmentation from our D2SAS D-loss channel. We could have D2 loss itself, so for the product DSAS or DSSI. We could also have contribution from a silicon plus D2S reaction because our SID molecular beam also has silicon in it. So I have 2 different fits of the data here. First, there are 2 peaks in the time of flight spectra. So here I fit with 2 different channels. The fast peak with our D2 loss channel and the slow peak with fragmentation. The next set of fits is with all 3 channels. However, even though this silicon plus D2S reaction is expected, it was calculated to have a maximum contribution of only about 3%. So from this, we can say that we do have the DSAS or DSSI D2 loss channel and also fragmentation from the D loss channel. So looking at the center of mass functions, first for the D2 SAS product, we can recover the reaction energy, negative 48 kilojoules per mole, which does match the calculated value. Looking at the angular flux distribution, we can see it is isotropic. So means we have an equal scattering probability in all directions, which can be visualized here in the flux contour map. Now we can look at the functions for the DSAS or DSSI product, which we recover a reaction energy of negative 146 kilojoules per mole. And this then matches the DSIS product, also isotropic scattering. So now, as a quick summary of what we have so far, in the silicon plus thiomethanol system, we can see the formation of the HSAS radical. And for the SID plus D2S system, we see the formation of D2SAS and DSAS. Now, I don't have time to go into all of the details, but for the partially deuterated case, the SID plus H2S system, we see similar results that support what we see for the fully deuterated system here. So now let's talk about the potential energy surface in this case. So this is a doublet surface for the SID plus D2S reaction. Here we have a collision energy of 15.9 kilojoules per mole. And with that collision energy, products P1 through P5 could be formed. However, our experiments show the formation of at least P1 and P3. So first we can start off with P3. With the pathway, we can see we have a barrierless addition of the silicon to the lone pair of the sulfur. After this, we could have a bond rotation, followed by a deuterium migration from the sulfur to silicon. And here we could have a deuterium loss to form P3, or we could have another deuterium migration followed by a deuterium loss. Now, if we look at the translational energy distribution, the most probable translational energy gives an estimate of the barrier height of our exit channel. And since this peaks away from zero, it indicates that there is an exit transition state. And so this way we can see that the highlighted pathway is the dominating pathway to form product P3. If we look at product P1, it follows the same pathway in which we do have this deuterium migration here, and then followed by molecular deuterium loss to form P1. If we look at the partially deuterated surface for SID plus H2S, we can see it's a lot more complicated. However, products P1 and P3 are formed through the same pathways as in the SID plus D2S reaction, which gives our previous conclusions full support. Our experiments were also coupled with astrochemical modeling in order to predict the possible abundances of H2SAS and HSAS in Orion KL. So the model begins with silane that has been thermally desorbed along with icy grain mantles. Silylidyne radicals can then be formed from silane through cosmic ray induced degradation or proton transfer followed by recombination with electrons. So at time t equals 0 in the model, the silane is introduced to the gas phase, and then we can see the chemical evolution over time. And so the derived column densities here are high enough that these species should be detectable, and the rotational frequencies of both species are known. So their transitions could be searched for in spectral line surveys of Orion KL. So to wrap things up, all three of these reactions involve barrierless addition, followed by dynamics involving atomic hydrogen or deuterium migration, and possible bond rotations before forming products through an exit transition state. The findings from the SID plus D2S system are confirmed with the partially deuterated SID plus H2S system. And modeling suggests the possible formation of H2SAS and HSAS in Orion KL. So even though they have not been detected yet, they are ready to be searched for. So I'd like to thank my PI, Dr. Ralph Kaiser, as well as other members of our research group. I'd like to thank those in Brazil for doing the computations, as well as Dr. Tom Miller for doing the modeling. Of course, thanking the funding agencies to make this research possible. And I'd like to thank all of you for listening to this talk.
Thanks, Shane. We have one question from Olivia Hartwick. What is the cause of the low signal to noise in the data for the SID plus D2S system?
Well, due to the, so we're making an SID radical beam. And so if it was in just the case with a silicon beam, the intensity is pretty high. But since we have a gas mixture of neon and deuterium, the bladed silicon then has to abstract a deuterium, which of course doesn't always happen. So that leads to a large decrease in intensity for our primary beam. And so this then causes our resulting product signal intensity to be much lower.
Thank you. Are there any other questions? You can either type them in the Q&A or raise your hand. David, it looks like Nesbitt, you have your hand raised. Chris, can you help me let him speak?
It says ask to unmute. Should be okay. David, you can go ahead and ask a question. If you can unmute yourself, you should be able to.
Okay, good. Can you hear me now?
Yes.
Yes.
Yeah.
Good. Shane, these are beautiful experiments. So congratulations. That's really quite remarkable.
Thank you.
If I can ask sort of a devil's advocate question, just because that's the sort of person I am, maybe. You know, when you interpret the exoergicity of a chemical reaction by looking at the essentially the velocity distributions, you know, in his wonderful angle resolved and mass to charge ratio resolved way, I would ask, you look at some cutoff and then you use that to get the exoergicity, assuming that that cutoff relates to no internal energy, vibration, rotation, or whatever in the product that you're looking at. And I want to ask the question. I honestly don't know if the dynamics would ever cause you to worry about this, but could there not be a case where, in principle, where there's really energy that gets so locked into the molecule that you're generating that you see sort of an artificial cutoff in the velocity distributions below your signal to noise level that might cause you to misinterpret what your reaction to exoergicity is actually proving to be. First of all, does my question make sense?
I think so, yes.
Okay. Is there any dynamical way? I mean, like, you know, it's quite possible that that would never happen, maybe, but is it ruled out sufficiently in your mind, you know, given finite signal to noise and things like that? That's really no criticism here whatsoever, just asking a question dynamically.
I believe you could be right. So if I were to go back, for example,
Good.
some of them seem to have a very, you know, finite drop in cutoff.
Right.
Yet sometimes they can be much more, you know, like a slow cutoff too.
Right.
So it's possible that we could misinterpret where the cutoff is, I believe, yes.
Right. Well, at any rate, it doesn't detract from the beauty of your experiments. They're just gorgeous. And thank you. Really very nice talk.
Thank you.
I think Ralph might have a comment on that. If you should be able to talk, Ralph. Or unmute yourself.
David, can you hear me? Hi.
A little quiet, but yes.
Yeah, I can hear you, Ralph. Go ahead.
Just a PS. So for reactions where the reaction energy actually matches the thermodynamically most stable isomers, we don't have this issue naturally, right? But in some cases, we published recently a paper, it's in press now, in JPCL. We did the reaction of C2 with silane. And Martin's group did the potential energy surface calculation. That's exactly where we see this problem. We have energy cutoff which does not match the expected value because too much energy is in the internal degrees of freedom. And this we could only figure out because additional dynamics calculations were conducted.
Okay, that's very interesting. Thank you. So the suggestion is not completely bizarre, but it's probably a rare influence for you. Yes?
I mean, the reason is, I mean, whenever we can find out where the HD, DH, H2, or HD comes from, if you can always do isotopically substituted experiments, we can always eliminate that. However, if all hydrogens are chemically equivalent, like in silane, we might run into this problem. And in C2 plus silane, we ran into that problem. So we always check that out.
Okay, great. Thank you. Thank you, Ralph. Thank you, Shane.
Thank you very much. So in the interest of time, I think we should move on. Shane, could you please stop sharing your screen?
Yes.
Thank you. And I'm delighted this afternoon to be able to introduce our invited speaker, Stefanie Milam. She's a planetary scientist at NASA's Goddard Space Flight Center, working in the Astrochemistry laboratory there. And she also serves as the James Webb Space Telescope Deputy Project Scientist for Planetary Science. She earned her PhD at the University of Arizona before moving to the SETI Institute at NASA Ames. She's an expert in rotational spectroscopy, observations, and laboratory modeling of astrochemistry, and her research includes the molecular astrophysics of the interstellar medium, stars, star-forming regions, protoplanetary disks, and comets, with an emphasis on isotopic fractionation and astrobiology of primitive materials. And today, she's going to talk to us about the James Webb Space Telescope. So without further ado, please take it away, Stefanie.
Thank you. Let me get rid of my floating heads. Stop distracting me. Okay, thank you so much for asking me to come and present today. And thanks to everybody for joining in. I'm going to give you a little bit of highlights about, what's going on with the JWST project and talk a little bit about some of the chemistry and a little bit about the observatory itself. And then hopefully we have time for questions in the end. As Heather mentioned, I'm the Deputy Project Scientist for Planetary Science at NASA's Goddard Space Flight Center in Maryland. And JWST is actually a joint partnership between NASA, the European Space Agency, and the Canadian Space Agency. This observatory was actually not even designed or conceived with the realm of chemistry in its at its birth. It was actually conceived basically to discover and search for the first stars and galaxies in our universe. This notion came out of the Hubble ultra deep field that was observed early on. So this is that image that was published. What happened was the director of Space Telescope Science Institute was really curious about what Hubble could actually do, what sort of the breaking realm of discovery space was for the Hubble Space Telescope. And so he allocated a lot of time actually from his own discretionary pool of time to stare at a region in space that hadn't really been investigated because most people thought that it was sort of a blank spot in the sky. Plus it was fairly close to the moon. And so from ground-based observations with larger telescopes, it was quite a challenging area to observe. And so they did this stare, and what they found was just absolutely unexpected and unanticipated. In this image, there's only a few stars, and they're obvious based on their sort of star-like radial profile. all these other dots and swirls and things are galaxies. And there are 10,000 galaxies in this postage stamp size piece of sky. And more importantly, we were able to determine how far away some of these galaxies were, even with the limited capability of Hubble going only into the near infrared. And what they found was, we could go back with Hubble by doing these long deep stares, or Chandra, and we could reach sort of maybe some of the first galaxies, but we're probably sort of in the realm of the let's say teenage years of the universe beyond the Big Bang. And so in order to go further back in time, they knew that they needed to go to longer wavelengths to accommodate further redshifts and get sort of the first stars and galaxies, or the toddler years of the universe, sort of after the cosmic white microwave background radiation and dark age expansion. So that is sort of where JWST was conceived. Now, this was before exoplanets were a thing. And this was sort of, pushing the capability of current infrared telescopes. And so there were a number of people that came on board to ensure that there was a good enough spectroscopy that we could actually do some molecular studies and get into the chemistry of some of these things, near and far. And so one of the highlight areas for actually studying chemistry with Webb is the whole star formation process. This is because JWST is an infrared telescope. So unlike Hubble, where dust and gas from large molecular clouds actually obscures light or anything within these large objects or behind them, as we go to longer and longer wavelengths, we start to be able to peer inside of them. And so you go from these beautiful optical images where you can't really see anything behind or within these objects to into the infrared, where we can actually start seeing now the birth of new stars and planetary systems, as well as objects that are behind these large dusty objects. So this is opening up a whole new realm of discovery space. Mind you, we have had infrared telescopes before, and space-based ones included, but none of them have had the sensitivity that Webb will have. The large aperture collecting area, new technology for detectors will really enable studies of some of these regions that we've really not had access to, mostly because with the sensitivity, we can now look at fainter background stars to study the gas and dust that's in front of them. And we don't have to depend on having a significantly bright object in the background. So this is going to give us more lines of sight, probing different regions across these clouds, as well as with the spectral capability, doing some studies that will hopefully be, rewriting the textbooks for astrochemistry. So one of the things that has sort of carried through the astrochemistry theme with Webb, as well as other space telescopes and ground-based telescopes, is sort of what our cosmic inheritance of volatile material is. And for space-based telescopes, one of the key molecules of interest is actually water, because it's so challenging to do from the ground. We can start probing things like tracers of waters with the ground, and even get lucky and do actual water lines with some of our ground-based facilities, but it's not always an option. Especially if you need various energy levels to be fulfilled from ground-based telescopes versus space-based, and technology with our detectors or cameras, spectrometers. These are things that have to be taken under consideration. But when you combine all the facilities of both ground-based and space-based, and even airborne, including SOFIA, you can really start building a comprehensive picture of the volatile content and how it's carried through from, say, a giant molecular cloud into cores, into protostars, into debris disk, and even all the way into the solar system by looking at some of the primitive bodies in the solar system. And the main contribution from JWST is actually going to be the solid component of this volatile material. Being able to determine how much of this volatile material is in ices is going to be a really key ingredient to understanding the full composition of these objects and how they evolve and the chemistry evolves. So obviously detecting molecules in star-forming regions is definitely a highlight and one of now JWST's key science themes. We have a handful of them, and obviously star formation and probing chemistry across the galaxy and the universe is something of significance for JWST. So by using Webb, we'll be able, and the spectroscopic capability from the near to mid-infrared, we're going to be studying all kinds of things, including mature stars with various sizes, mass, age, color, etc. The new stars, as I just discussed, that are embedded within these deep, dark clouds. Cold molecular clouds that actually start the collapse to form some of the stars, especially small stars. And then the gas and the dust that's ejected from dying stars. So following this full stellar life cycle. And not to even mention all the stuff that's in between the stellar life cycle and including things like planetary systems. So this is a fantastic simulation that was done at Space Telescope Science Institute of a simulation of a protoplanetary disk. So now we're going from, this interstellar composition where we can sort of probe sight lines of star forming regions to now start probing the chemistry across a disk and seeing what that composition may or may not be. You can see in the mid-infrared with Webb, we actually cover a lot of different molecular bands of interest of key volatiles, including things like carbon dioxide, which we don't have access to from the ground, but also other species that are challenging from the ground, including things like methane and access to ammonia lines. But if we start talking a little bit more in detail about molecular inheritance and trying to trace this back into the whole planet formation, including things in our own solar system, we have a lot of processing that we have to be able to understand. And this is where having complementary observations coming from multiple facilities, multiple wavelengths, and multiple objects is really going to be key to get a better understanding of the processing that may or may not be occurring in some of these objects and how that chemistry may or may not be preserved as we get into planet formation. So primitive bodies in our solar system are considered, fairly pristine, but we also have to think about all the complexity that comes about as these objects were actually formed and how that chemistry could or could not be affected. So thinking about things like migration and transport from the inner disk to the outer disk, seeing how that chemistry could be altered just through thermal properties of the disk, radiation coming from a protostar, external radiation such as cosmic rays that are penetrating the disk, and then what may or may not be preserved, say in the ice in the midplane of the disk, especially in the outer regions, and how much of that is actually preserved in some of these primitive bodies. These are going to be essential, but also things that we're going to be able to start studying in excellent detail, again, by surveying multiple disks, getting a full compositional study with multiple facilities, and then comparing that to things like primitive bodies in our solar system, like comets. I showed you a mid-infrared simulated spectrum, and this is sort of a near-infrared cometary spectrum going from about 2 to 5 microns. And this is a simulation with a spectral resolution of about 3,000 of some of the major comet volatiles that you would expect to see. What's important to note is while we have near-infrared capability at a lot of facilities from the ground, we will have the access with JWST to some species that, as I mentioned before, we can't actually observe from the ground, like carbon dioxide, which is actually critical for some of the volatile material that's being preserved in the outer solar system, for example, in comets. While we've studied comets at these wavelengths, and we continue to do so, and we've had a number of missions to them, we haven't always had the spectral capability or sensitivity that Webb will have. A flyby mission is fantastic because you get the proximity, so you don't necessarily need a large telescope. But unfortunately, you're only observing one object, and sometimes it's not even active, just due to the nature of a flyby mission. So what you're seeing in this dark green line is actually a spectra that was acquired from the Deep Impact mission towards 9P Temple 1. This spectrometer, while it was fantastic operating across the full near infrared, it had a very limited spectral resolution of only about 100. And with that, you get sort of this water band at the 2 to 3 micron region, the carbon monoxide / carbon dioxide band around 4 to 4.5 microns, and then the quote organics band around 3.5 microns. Not being able to really discertain what organics are comprised in that particular feature, and being able to disentangle the carbon monoxide, carbon dioxide abundance at these wavelengths. So with Webb, we're actually going to get clear studies of some of these molecules, not only just the detection of them, but also some resolution that we can actually determine things like temperatures and densities of some of these molecules. So this is going to open up a whole new world. And with the sensitivity of Webb, we're actually going to be able to study snow lines within our own solar system. So actually watching and monitoring objects as they're coming into the solar system at large heliocentric distances, or distances from the sun, we can see when sublimation of some key volatile species and comets actually starts turning on, and monitor these snow lines of these objects as they come in and out of the solar system. This is something the sensitivity of most ground-based telescopes, and even just their limited capabilities of only nighttime observations, is really quite challenging to do from the ground. Not to mention that we can't do carbon dioxide. So these kinds of studies are going to be very interesting and give us a lot of insight into our own snow lines and disk in our solar system, and how that might compare to other disks and other objects in our galaxy. We can also do some pretty cool stuff, like do some isotope ratios of volatiles. The carbon-13 carbon dioxide species is something that we haven't been able to measure in comets. And so this is of key interest to be able to do with Webb with its sensitivity. We'll probably need a pretty bright comet, but I think this is going to be a really interesting result and actually reveal a lot about the volatile chemistry and preservation of some of these species. And of course, there's the whole discovery space in small bodies in the interstellar medium, in star forming regions, et cetera, with Webb, because we cover wavelengths that are not accessible from the ground, and we have the sensitivity and spectral resolution. We can start doing some searches for some really interesting molecules. So one particular program that I want to highlight is by my group for cycle 1, where we're actually going to be searching for polycyclic aromatic hydrocarbons in a comet. These have been claimed to be detected previously from other observations, but never confirmed. So with Webb sensitivity and wavelength coverage, we can actually start probing this at a nice intricate detail and understand what's happening as far as the complex carbon chemistry in some of these primitive bodies. And not to mention, we now have interstellar objects, which are a whole nother world of astrochemistry, understanding where they come from, what their composition is, and whether or not they're tracing their own disk, or if they've been processed on their journey through the interstellar medium. So there is actually a program in place, again by my team, to do a targeted opportunity search and study of an interstellar object as it comes available during Webb's lifetime. This is going to be challenging for us because Webb's field of regard is a little bit limited because of the shape of the observatory, but hopefully we'll get something that comes within the field of regard and we can actually observe one of these objects. So as we talk about other planets, as I mentioned earlier, exoplanets were something that were discovered during the whole formulation of the Webb project. And so we had to actually redesign and consider how to study exoplanets as the mission and instruments were being worked. So Webb has actually now made exoplanet science one of its priorities and major goals to do studies of some of these exoplanetary systems. So we have implemented coronography. So this is where we actually block or occult the star with a instrumentation, which basically allows us to detect fainter objects in the vicinity of that object by blocking it out. At these wavelengths, planets are fortunately quite warm and very, very bright in the thermal infrared. So this will be a nice opportunity to do some studies of coronography of exoplanets in our galaxy. And then, of course, there's also transit spectroscopy, which has been quite successful for space-based missions, for example, with Spitzer and the Hubble Space Telescope. So through this, the planet actually passes in front of, the planet actually passes in front of its star, basically dimming out the brightness or the flux coming from that star. And the bigger the planet is, the deeper the curve goes. We can also do things like compositional studies as planets pass in front of their stars. We can study their atmospheres and determine what the composition of these atmospheres are, as well as do other things like refine orbits and do other characteristic studies of exoplanets. One hot topic, of course, and something we get asked quite often about Webb is what are we going to be doing for habitable worlds? And that's an excellent question. And we have quite a bit of challenges put forward. We really need a larger telescope. And as the Astro 2020 came out, you see that that was actually prioritized as well. So hopefully the new LUVX, I think is what it's being dubbed as, will enable opportunities for studying habitable worlds on a much more sophisticated level. But that being said, Webb is still going to enable a lot of preliminary studies and help us sort of refine what should be done with follow-up observatories in the future. We do have access to wavelengths of key species. So this is actually a spectrum of Earth. And you can see some of the molecules that we would see sort of in a planetary habitable world, such as our own, instance one of an Earth-like planet, that we could actually start searching for in other planetary atmospheres. So looking for things like water, oxygen, carbon dioxide, methane, et cetera. We can actually start studying the composition of some of these planets and get a better understanding of which planets may or may not have chemistry that's not in equilibrium, possibly caused by some process on that planet, be it geologic or biologic, altering the atmosphere in some manner. It is also important to note that just because we see something obscure in a planetary atmosphere, it does not mean that it's life. We have to remember that planets evolve just as much as we have as humans. And so the atmosphere will be dynamic and changing throughout a planet's lifetime. Think about large impact events, storms, geologic processing, et cetera. These are all things that are going to alter that atmosphere. So just because we don't find a quote Earth 2.0, that doesn't necessarily mean there isn't one. And this is just something. While we're talking about planets, we should also remember that planets aren't all like Earth. We have a lot of interesting chemistry going on within our own solar system and our own planets and satellites. So in the first year of observations with JW, sorry. Okay. We have a full suite of programs that cover everything from Mars, small bodies, all the way out to the outer solar system, including objects like Pluto and some of the other trans-Neptunian objects. We're going to do fun studies like looking at composition of plumes of ocean worlds. With the resolution of Webb, we can actually study Europa in a nice detail, basically taking spaxels across the disk of the satellite. So each one of these squares, we get a full near infrared spectrum. So we'll be able to characterize not only the plumes, but also the surface and any deposits that may be residue or whatever evident of activity across the surface of one of these bodies. I'm going to briefly talk about the telescope. I know I'm running out of time, so I'll try to make this quick, but if you have questions, we can certainly address them. Webb is a huge telescope. That's the in a nutshell summary of it. And because it's so big, we had to do a lot of things to make sure we could actually launch it into space and operate this telescope in 1 million miles away from Earth. So just for context, we have a 6.5 meter diameter primary mirror compared to the Hubble Space Telescope mirror, which is only about 8 feet. I'm a below average person, so I always like to put into context what I actually look like compared to a standard human, as well as next to the JWST mirror. It is quite impressive, and I can tell you I have stood next to it, and it's something quite spectacular. We have some primary components and noticeable parts of the telescope, including this huge sunshade that's about the size of a tennis court, our beautiful gold primary mirror, but then we also have the heart of the telescope, which resides right behind the primary mirror, where we have our 4 science instruments. These 4 instruments were contributed from all of our partners. We'll start with the mid-infrared instrument, which offers imaging and spectroscopy from about 5 to 28 microns. This was provided by the European Space Agency with contributions from JPL. The near-infrared camera is our workhorse instrument. This is not only how we focus our telescope and optimize our mirrors, but it's also our primary imaging instrument. It offers wide field deep imaging from 0.6 to about 5 microns. And it was provided by the University of Arizona. The fine guiding sensor and near-infrared slitless spectrograph was provided by the Canadian Space Agency. And this is an instrument that was designed and optimized for exoplanet science so that you could do a full near-infrared slitless spectrometry on exoplanets with a resolution of about 150. And our workhorse spectrometer is our near-infrared spectrometer that was provided by the European Space Agency, offering all kinds of spectroscopy, including multi-object spectroscopy, SLIT, and IFU. As I mentioned, Webb's going to be 1 million miles away from Earth. It's going to be in orbit around the second Lagrange point. This means that JWST is always on the anti-sunward side of Earth, but we always have access to the sun for our solar array, for power, and we always have access to the Earth for communications. We're never in the Earth and Moon shadow, so we don't have to worry about any access to the sun. This is again sort of what the observatory looks like. So we have a sunward facing side, which gives us our access to the sun and Earth with our communications and all of our control and star trackers. With an SPF of 1 million sunshade, we actually, our sun shield, we get to the cold side of the telescope where the mirror and the instruments reside. We have to fold this massive beast up. Unfortunately, we don't have a rocket big enough to put a 6.5 meter diameter telescope into. So we fold it up like origami so that it fits in the fairing of an Ariane 5 spacecraft, or rocket, excuse me. And this is what it looks like when it's stuffed inside of there. Which that also means we launch in a folded up configuration. We have 1 month to get to L2, or 1 million miles away, and we have 1 month basically to unfold the telescope. This is done in a very systematic way where we are constantly monitoring the temperature of all components of the observatory to make sure contamination like ice or dust from the launch itself, or that's residing within the fairing, does not freeze and condense onto any of the surfaces as we cool down. Last month, we went from California, Northrop Grumman, all the way down to French Guiana to our launch site. We went by cargo on a shipping container and went through the Panama Canal successfully. And we have since arrived at Arianespace and unloaded the telescope from its shipping container and have begun cleaning and doing final inspections. I hope you learned a little bit about some of the exciting discoveries of Webb, but I assure you that everything I presented is only the top of the surface. There's definitely going to be far more discoveries than we can even imagine at this moment in time, and hopefully the next generation of astronomers will lead us to them. We have a 5-year primary mission, which is what we're required to have. from NASA, but we're also required to carry 10 years worth of fuel. With efficient operations, we're expecting to operate the telescope for probably about 12 years, which means young scientists today have the opportunity to use this observatory. And with that, I'll take any questions. Thank you for your time.
Do we have any questions? Chris, do you have your hand
Yes,
raised?
I have a quick question. Actually, you answered a lot of the questions I had as you went along, which is, so thank you. But regarding the coolant and the temperature, one thing that I was, actually someone asked me about this and I didn't know the answer, so I can pass it on to you. Since the detectors are cooled, right, with cryogen for the infrared, is there any danger of volatiles condensing either on the primary mirror or the detectors that could pose a problem? Is that something that people have thought about, that there's some kind of way to heat it or something like that?
Okay, so there's only one instrument that's cooled, actively cooled. We do have one cryo cooler to cool down the mid-infrared instrument. It needs to be below the 40 Kelvin that everything else on the cold side will actually be operating at. 40 Kelvin is cold enough to condense a lot of volatile material, but that's, as I was saying, as we depart the rocket and eject the fairing and casing, we have a lot of gas and dust that's probably going to be captured within that whole rocket blast and exiting Earth's atmosphere. And so we don't even begin to start triggering of our full deployments until after we pass the moon. So we have quite a bit of time to actually gas and release some of that gas and dust, and hopefully as we start the unfolding process or the unfurling process, we will be monitoring the temperature enough such that we'll make sure that potential risk of, all the areas get warm enough, but also as they start cooling down, that we're in a lower risk environment to start condensing anything onto the surface.
Yeah, okay, thank you.
Dust are definitely our primary concerns for contamination. And
So
we do have heaters on our instruments so that we can heat them if ice does build up on any of the instruments themselves.
when is the launch date and deployment date?
Launch is December 18th. So we are, 37 days away, something like that. So we're getting very, very close. We're down at Arianespace, as I said. We've unloaded everything and started integration. Cleaning, we're finishing up cleaning, and we'll start integration with the rocket fairing pretty soon. We'll also be fueling the tanks with the fuel. So that is sort of the point of no return for the spacecraft ever returning to the US. So we're very close. And it's a month long for our journey to the second Lagrange point.
Someone also asked, why was gold used as the primary mirror rather than another metal?
So the mirror itself is actually made out of beryllium. It's hollowed out, sort of bored out beryllium. You can think honeycomb structure sort of on the backside of the mirror, and with a single thin layer that's been polished and optimized at 40 degrees Kelvin. And then we basically did a gold vapor deposit. So the amount of gold covering the full 18 segments when condensed down is actually only about the size of a golf ball. Gold is very, very reflective in the near to mid infrared. So that's why we have a gold coating.
One person at Thomas Carroll asked, do you expect to resolve rotational structure?
Not really. Maybe in some molecules, but not most of them, no. At a resolution of 3000, it's not really optimized.
Okay, and then Susanna Weaver asked, could you share some of the highest priorities of lab needs with this very chemistry-based audience?
With lab needs, sure, I can try, but hopefully the laboratory community can also help me with this. So some of the key things that we've already identified that we need for JWST are things like optical constants of ices, understanding how some of the ice processing may or may not be occurring. We also need theory in some of this, as well as some new species, maybe predicted, telling us which molecules that we should or should not be looking for. There's other laboratory needs that need to be done, especially in the field of exoplanet science. We have a lot of laboratory spectra for sort of the interstellar medium right now, but high temperature sort of photosphere or planetary atmosphere of hot Jupiters, for example, is something that's not mostly not even measured, and a lot of molecules that will start that JWST will be able to search for in exoplanet atmospheres, but even moving forward into the next generation as we study more and more planets. There's a number of other things that obviously need to be done just in general for laboratory astrophysics, but will only help improve the quality and data return of Webb, like cross sections of various species, and now getting into beyond the hydrogen cross section regime into more things like water. I guess I could go on and on. I can point to a number of white papers that have been submitted about laboratory astrophysics needs for Webb, as well as for the community over the next decade.
Dave Nesbitt asked, are the spectrometers in the various spectral regions all grating plus array detector based, or are there other dispersion mechanisms like FT?
There's no FT. They're all mostly grating. So yeah, they're not, we don't have the space or mass.
Okay. Ryan Fortenberry asked, when will the initial cycle 01 data archive be released to the public?
So there's going to be multiple sort of releases as we go. There's a number of programs that are actually already open to the public as soon as the data become available. So there's no proprietary period assigned to some of these programs. Primarily, those are what we call our early release science program. So as soon as these observations occur, they will be, once they go through a quality check, they will be released to the public. And that was to ensure that everybody in the community has access to cycle 1 data prior to the cycle 2 call for proposals. There's also a number of guaranteed time programs that have waived proprietary periods for their programs. I will say most of the solar system science has actually waived their proprietary period. And a number of other significant fields for the astrophysics community has also waived that proprietary period. So those will become public as soon as the data are acquired and verified. Otherwise, everybody was given in cycle 1 the opportunity to have 1 year proprietary period on their data. Once that year is up after delivery of their data, then it becomes public and put on the Mikulski archive where the Hubble Space Telescope data resides.
Okay, and then last question, I think. Stephen Farber asked, how broad is the field of view and how widely can it be varied?
That's a great question. We don't have a very big field of view. You can think of sort of Hubble Space Telescope scales, so a few arc minutes at best with our largest imagers. So we're not a surveying telescope. We're not going to be hunting for Planet 9, for example, which would be great if we could, but we just don't have the field of view to do so. Fortunately, our next big mission for astrophysics at NASA is a wide field infrared surveying telescope known as the Roman Space Telescope, which has a significant large field of view, 100 times that of the Hubble Space Telescope. So while we only have a limited sort of area to observe at a time with JWST, we certainly have the sensitivity to do detailed studies. But if we want to do searches for objects, for example, or wide imaging kind of compositional studies, that's something that we'll have to wait for the next best thing, the next observatory.
Thank you so much for your presentation, Dr. Stefanie Milam, and also thank you, Shane Goettle, for your presentation earlier today. Thank you all for joining us for the AstroCheminars. We will be back in January. We're going to take December off because of Pacifichem. So we will see you back here. Dr. Ann McCoy will be our invited speaker in January. Thanks so much. Bye.
Thank you.